You know, what if the real secret to making a super smart AI isn't about finding that one single perfect model? What if instead it's about building an entire all-star team of them? That's the powerful idea we're diving into today, how combining models can create something far smarter and way more reliable than any single one could ever be on its own.
And that's really the core question, right? I mean, think about it in real life. A single expert, no matter how brilliant they are, they've got their own perspective, their own biases, maybe a few blind spots. But when you get a team of experts together, well, they can cover for each other, they can challenge assumptions, and they can come to a much more solid conclusion. It turns out the exact same principle is a powerhouse in machine learning.
And look, this whole team idea, it's not just some nice way to think about it. In the world of data science, this is a formal strategy, and honestly, it's a total game changer for getting top-tier results.
Okay, so there's a name for this stuff. They're called ensemble techniques. The concept is actually pretty simple, but it's incredibly profound. You combine multiple machine learning models to create one single superior predictive model. You're basically leveraging the individual strengths of each team member, and at the same time, their individual weaknesses get averaged out and minimized. The result? A whole that is truly greater than the sum of its parts.
So if we're gonna build these model super teams, how do we actually do it? Well, it turns out there are a few key strategies, or you could call them plays, in the Ensemble playbook. Let's break down the main ones to see how they tick.
First up, we've got something called bagging. Okay, imagine you're trying to guess how many jelly beans are in a giant jar. Instead of asking just one person, you ask 100, but you only let each person look at the jar from a slightly different angle. That's kind of like bagging. Each model gets trained on a different, random little piece of the data. Now, the key insight here is that while each model might make a mistake, their errors are usually different. So when you average out all their guesses, those random errors tend to just cancel each other out. This is fantastic for reducing the risk of overfitting. That's when a model basically just memorizes the answers for the test, but then completely bombs when it sees a new question it's never seen before.
Next up is boosting, and this one takes a completely different approach. See, with bagging, the models all train independently at the same time. Boosting is a sequential process. It's more like building a team of specialists, one by one. The first model makes its best guess. Then the second model comes in and trains specifically on the mistakes the first one made. Then the third model focuses on correcting the errors of the first two combined, and on it goes. It's a process of continuous, focused improvement where each new team member is basically an expert on the team's past failures.
Then there's stacking, which builds a different kind of team entirely. Imagine you have a really diverse group of specialists. Maybe one model is simple and great at spotting basic trends, and another is a super complex neural network that's amazing at finding hidden patterns. Stacking trains all of them on the same problem, takes their individual predictions, and then feeds those predictions into a final meta-model. This meta-model acts like a savvy team manager, learning which of its specialists to trust under which conditions to make the best possible final call.
And last but not least, you've got the most straightforward method of all, voting. And yeah, it's pretty much exactly what it sounds like. You train several different models, you let them all make a prediction on the same data, and the final answer is simply decided by a majority vote. It's simple, it's democratic, and you would be shocked at how often this simple approach delivers incredibly effective results.
Okay, so we've seen the playbook. Now, let's zoom in on a real legend, a true heavyweight champion from that boosting family, an algorithm that has become famous in data science competitions for its sheer raw power.
Meet XGBoost. Now, don't get hung up on all the text on this slide. We're going to break down what you actually need to know. The main thing is this. If you follow the world of competitive data science, you have absolutely heard this name. For years, it has been the champion, the go-to algorithm for winning competitions that use structured, tabular data.
So what is this thing? Well, the crucial point is that XGBoost isn't some fundamentally new idea. It's an extreme and ridiculously optimized version of that gradient boosting framework we just talked about. In fact, the XG in its name literally stands for extreme gradient. It takes that core concept of sequential error-correcting models and just engineers it for maximum speed and accuracy.
But okay, what's the secret sauce? What's actually going on under the hood that makes this thing so consistently powerful and so dominant in its field?
So what are its superpowers? Well, for starters, it is built-in regularization. Think of these like bumpers in a bowling lane, just keeping the model from going off track and overfitting. Second, it's engineered for parallel processing, which is a fancy way of saying it's just wicked fast because it can do a bunch of things at once. Third, it uses intelligent tree pruning to snip off useless branches from its decision trees, keeping the model lean and efficient.
Fourth, and this is a huge advantage for messy, real-world data, it handles missing values all by itself. And finally, it has cross-validation built right in, so you can check how it's doing as it trains. It's really a complete, battle-tested package.
So let's just quickly walk through how it works. First, it makes a simple baseline guess. Then, it starts a loop. In each step of that loop, it builds a brand new decision tree, and that tree's entire job is to predict the errors of the current team. It then adds this new error-correcting tree to the group, updates the overall prediction, and just repeats the process, getting smarter and smarter with every single iteration.
But of course, like any high-performance tool, this kind of incredible power doesn't just come for free. There are always trade-offs you've got to consider before you decide to unleash it. And here's the breakdown, side by side. The advantages are just undeniable. You get state-of-the-art accuracy, impressive speed, and it's flexible enough to handle gigantic data sets. But the disadvantages are very real. It can be computationally intensive, meaning it can be a real hog for memory and processing power. And getting that top-tier performance requires careful and often pretty complex tuning of its many parameters. Those are just the internal settings that control how it learns. It's a high-performance engine, and it really needs a skilled mechanic to get it running at its best.
So this leaves us with a really critical strategic question. We know that these powerful teams, especially champions like XGBoost, can deliver incredible results, but they also demand more resources and more expertise. So the question for any data scientist, for any project really, becomes a strategic one. For your specific problem, is the incredible power of a complex team really worth the price of building and maintaining it?